perfection would have been silent. A perfectly symmetrical universe, balanced in every direction, equal in every charge, could never have moved, cooled, or created. Nothing within it would have favored one interaction over another, and no clock would have begun to tick. What we call existence depends on the opposite. The smallest cracks in balance, minute departures from symmetry that transformed timeless equilibrium into a cosmos in motion. It is this quiet flaw, this graceful imperfection, that gave birth to everything that spins, shines, and lives. In physics, symmetry expresses a rule. When the laws of nature remain unchanged under a transformation, such as rotating a system, shifting it through space, or reversing direction, the universe is said to honor that symmetry. These invariances underpin all known forces. But complete symmetry, unbroken and eternal, would forbid evolution. A system without asymmetry has no reason to change. Energy would remain evenly distributed. Matter and antimatter, paired perfectly, would annihilate in mutual cancellation. Light would expand uniformly until it lost meaning. Time's arrow would never emerge. Reality's first act was therefore a breach of evenness, a spontaneous division of what had been identical. The record of that event remains imprinted across cosmic history. When the universe was less than a second old, its temperature exceeded 10 billion Kelvin. At such densities, all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear interactions, were unified in form. As expansion cooled the fire, they began to separate in a series of phase transitions called spontaneous symmetry breaking. Each split produced slight irregularities in energy, allowing structure to appear. Gravity gained independence and began shaping space-time. The strong force bound quarks into protons and neutrons. The weak force introduced asymmetry between matter and antimatter, deciding that one would prevail. Those microscopic imbalances are visible today as faint variations in the cosmic microwave background, the afterglow of the Big Bang. Satellites such as WMAP and Planck have mapped its temperature to 1 part in 100,000, revealing an almost uniform cosmos punctuated by subtle differences. These ripples of density, only millionths of a Kelvin apart, served as gravitational seeds for everything that followed. If the background had been perfectly smooth, galaxies would never have condensed. Matter would have remained diffuse gas for eternity. The beauty of imperfection lies here. Structure exists only where symmetry fails. Among the most consequential asymmetries is the one known as baryon asymmetry, the slight excess of matter over antimatter in the early universe. For every billion pairs created, one extra particle of matter survived the great annihilation. That fractional remainder became the substance of all stars, planets, and observers. Why the imbalance occurred remains uncertain, but laboratory experiments have uncovered hints. In 1964, researchers James Cronin and Val Fitch observed a subtle violation of CP symmetry, the rule combining charge conjugation and parity, in the decay of neutral kaons. Their discovery revealed that nature distinguishes between left and right, matter and antimatter. This minuscule preference ensured that destruction was incomplete, allowing a residue sufficient for worlds. The breaking of symmetry also defined the direction of time. According to the second law of thermodynamics, processes evolve toward greater entropy, producing an irreversible arrow from past to future. If the universe had begun perfectly uniform, no gradient would exist to drive change. The first irregularities in temperature and density therefore created the conditions under which time could progress. As the physicist Sean Carroll once noted, the arrow of time is born from the universe's low entropy beginning. In that sense, imperfection did not simply permit time, it created it. Even matter's most elementary properties owe their stability to broken symmetry. When the Higgs field acquired a non-zero value, roughly 10 to the power of negative 12 seconds after the Big Bang, it diversified the previously massless particles of the early universe. Electrons, quarks, and neutrinos gained distinct identities. Without this field, and its subtle departure from perfect symmetry, no atoms could have existed. Each element, each chemical bond, and every molecular form is a continuation of that primordial deviation. Hey everyone, thanks for stopping by. If you enjoy the content we shared today, don't forget to hit that subscribe button. As the universe matured, its imperfections propagated across scales. Hydrogen clouds collapsed asymmetrically, spinning faster as they condensed into stars. Among them, heavy elements were forged through fusion and supernovae, scattering unevenly through the interstellar medium. That uneven enrichment seeded planets with different compositions and temperatures, setting the stage for chemistry and, eventually, biology. Every contrast, hot and cold, solid and void, is an inheritance of imbalance. Life itself expresses this principle at the molecular level. The compounds essential to living organisms exhibit chirality or handedness, mirror image forms that cannot be superimposed. Amino acids, the building blocks of proteins, exist almost exclusively in a left-handed configuration. Sugars within DNA and RNA twist to the right. This bias is universal across all known species. Laboratory synthesis of amino acids produces equal mixtures of both forms, yet biological systems selected one side somewhere in deep prehistory. The cause remains debated, but many researchers suspect that chiral light, circularly polarized ultraviolet radiation passing through magnetized dust clouds in the early solar system, destroyed one form slightly more efficiently than the other. If so, the preference for left-handed molecules on Earth may trace back to cosmic asymmetry burned into the light of ancient stars. The same pattern recurs throughout physics. Particles, forces, and even light exhibit asymmetrical behavior. Neutrinos, all but massless, are observed only in left-handed spin states, whereas possible right-handed counterparts remain elusive. Magnetic poles never exist in isolation. Their duality, north and south, embodies broken symmetry expressed through field lines. Galaxies, too, reveal statistical biases in rotation direction across cosmic expanses, suggesting large-scale alignment inherited from early conditions. Each of these phenomena adds weight to a single conclusion. Perfection is not the source of order, deviation is. For theoretical physicists, symmetry and its breaking provide the grammar of natural law. Noether's theorem, formulated in 1915 by mathematician Emmy Noether, states that every continuous symmetry corresponds to a conserved quantity. Rotational symmetry preserves angular momentum. Translational symmetry preserves momentum. Temporal symmetry preserves energy. When a symmetry breaks, the associated conservation gives rise to new dynamics, new fields, new possibilities. The diversity of the cosmos is therefore the history of symmetries lost, and in their loss, new freedoms gained. The concept extends even to perception and aesthetics. Human sensory systems evolved to detect variation, edges, contrast, deviation from uniform tone. Pure homogeneity conveys no information, while difference communicates meaning. The same neurological bias that allows us to discern melody among noise or pattern among randomness reflects the deeper structure of the universe. Consciousness, at its core, is tuned to asymmetry, because without differences through time and space, awareness itself could not change. In recognizing imperfection, life recognizes existence. Astronomical observation confirms that asymmetry continues to shape the large-scale universe. Spiral galaxies display richer structures in one arm than the other. Clusters form filaments rather than spheres. Even the expansion of the cosmos accelerates unevenly under the influence of dark energy. None of these irregularities signifies disorder. Rather, they reveal a system perpetually adjusting curvature and flow to maintain balance. The apparent imperfection of cosmic design is what allows continuity across time. This notion finds eloquent expression in the mathematics of chaos. Non-linear systems, weather, tectonic motion, biological populations, operate under deterministic laws, yet remain unpredictable because small differences amplify over time. Still, within the turbulence lie recurring patterns called attractors that confine possibilities within bounds. The world's unpredictability, derived from initial asymmetry, is precisely what keeps it alive. Static perfection would have been fatal. Dynamic imbalance sustains diversity. From a philosophical vantage, the beauty of imperfection lies in its universality. From galaxies to molecules, asymmetry guides evolution without intention. It is the principle that transforms potential into actuality. In theology and art alike, creation myths often describe an initial disturbance, a word, a movement, a separation of light from darkness. Science has translated those metaphors into measurable events: the spontaneous breaking of symmetry, the birth of distinction. Whether spoken by deities or dictated by quantum fields, the narrative is the same. Being emerges when balance yields to difference. Even now, the instability of perfection drives the universe onward. The same vacuum energy that gives rise to expansion may one day fluctuate again, triggering a new phase transition and a different pattern of laws. Cosmologists speculate about epochs of symmetry breaking preceding our own, cycles in which universes are born and re-equilibrated by imperfection. Each new cosmos would carry unique parameters, different masses, charges and constants, emerging not from design but from the probabilistic freedom that asymmetry allows. The implications reach the human scale with poetic resonance. Every organism, every landscape, every artifact carries marks of variation. Fingerprints, fault lines, irregular heartbeats, asymmetrical faces. The Japanese aesthetic of wabi-sabi celebrates this transience and imperfection as the essence of beauty. In the same spirit, physics reveals that imperfection is not a flaw intruding upon order, but its prerequisite. The planetary tilt that gives us seasons, the random mutations that generate new species, the small instability that ignites a star, all are imperfections woven into necessity. In view of this, perfection would be sterile. Only through deviation can the universe test possibility, and through imbalance, it constructs continuity. Nature's asymmetry is the ongoing dialogue between chance and law, equilibrium seeking itself through change. To observe a mountain's erosion, a seed's germination, or a galaxy's spiral is to witness imperfection functioning as purpose. Without it, we would have no notion of time, no structure to experience, no observers to contemplate the question. Thus, the universe's grace resides not in flawless symmetry, but in the sensitivity of its departures. The slightest inequality between matter and antimatter produced the visible world. A tiny deviation in expansion rate allowed galaxies. A minute asymmetry in molecular spin generated life. These are not accidents of imperfection. They are the signatures of creativity itself. When we trace every cause backward to the first seconds of existence, what we find is less an explosion than a silence broken by imbalance. A smooth field trembled and chose a direction. That tremor became gravity, atoms, and light. It became the rotation of planets and the heartbeat of living things. In every asymmetry lies the origin of motion, and in motion, the possibility of memory. Perfection remains an idea, the dream of stillness. But the universe had no need for perfection. It required only the willingness to be incomplete.